Hello students, welcome you all. In my today's lecture, I will explain the introduction and instrumentation of mass spectrometry. So this is one of the analytical technique and it gives the information about the molecular mass of any unknown compound. So we have seen the IR spectroscopy, NMR spectroscopy and this UV visible spectroscopy. So in UV visible, what we have seen, the different electronic transitions, like it tells about the N to pi star transitions, pi to pi star transitions, sigma to sigma star transitions, various transitions in a molecule which are possible. Whereas in IR spectroscopy, we study about the if any type of functional group is present, if OH, NH or some SH, C11C, in different functional groups are present, that gives the information. Whereas in NMR spectroscopy, different types of proton, different types of carbon atoms present in a molecule, that we get the information. But here in mass spectrometry, what it tells about the molecular mass of an unknown compound up to a certain limit, suppose up to 1000 Dalton. So the main purpose of this technique is giving information. It tells about the molecular mass. And another thing that here it differs from the other spectroscopic technique. Here I have written mass spectrometry instead of spectroscopy. So because in other spectroscopic technique there is the absorption of radiation. Here there is no absorption of magnetic radiation. Okay, but absorption of electron, beam of electron occurs, or we can say the beam of electron is bombarded on the molecule. Okay, then we study that gives after that it gives the information. So no absorption of radiation takes place in this technique. No absorption of electromagnetic radiation. Okay. Instead, a molecule is bombarded with a beam of electron. Instead, a molecule is bombarded beam of energetic electrons. Okay. And next thing, one of the important points, later we will see in detail also, the mass spectrometer, it only observes the main point, it only observes the any molecule in the form of cation. Okay, means a neutral molecule is not observed by the mass spectrometer, or anions are not observed by the mass spectrometer. So mass spectrometer analyze the only cations. Only analyze, or we can say detect, the cations. Okay. So no anions or neutral molecule is detected. No anions or neutral molecule is detected. Okay, so it is designed in such a way. So the spectrometer is designed in such a way that it only detects the cation. If it is designed in such a way that it may detect the anion, but the design is such a way that it only observes the cation. Then we will see in an instrumentation part also. Okay, so so what happens in mass spectrometer? Suppose if we have a molecule, and then this molecule, what I told, this molecule, it is bombarded with beam of electron. Okay, at suppose 10 to 15 electron volt. So what will happen? So the molecule will get ionization. So ionization will occur. So after bombardment, ionization of molecule takes place. Now further, this ionization takes place at 10 to 15 electron volts. So for ionization, this much of voltage is sufficient. Now if it is at high voltage, suppose at 70 electron volt supply, this ionized molecule that will undergo fragmentation. So fragmentation of ionized molecule takes place. Okay. And then this fragmented molecule, various fragments, molecule will be converted into various fragment, and fragment is then detected by the mass analyzer. So fragments are then detected by mass analyzer. Okay, these fragments are detected by mass analyzer when the signal is amplified, and then finally recorder, it gives the spectrum, mass spectrum is given by the recorder. Okay, so now suppose if M is the molecule, and this molecule is then bombarded with an electron, energetic beam of electron, and what I told you, at 10 to 15 electron volt. Suppose at this occurs at 10 to 15 electron volt, and ionization takes place, so it would be converted into various this ionized. So M plus, actually this is now converted into, this is a neutral molecule, and mainly we should write neutral gaseous molecule. Better to write neutral gaseous molecule. Suppose if a molecule is in solid form, then first of all it should be converted into gaseous molecule, then it would be bombarded with the electron. If molecule is liquid, then that is converted into gaseous form, then that would be, after vaporization, it would be bombarded with the electron. And suppose if it is in gaseous, already it is in gaseous form, then it could directly be bombarded with the electron. So this is the molecular, we can say this is one of the radical is present, and this positive sign is present. So this is a radical cation. So this is our radical cation, and this is also called as the molecular ion. This ion is also called as the molecular ion, or this is also called as a parent ion. Okay, now this molecular ion is then further, it is bombarded with electron at, suppose at 70 electron volt, and at this 70 electron volt, this molecular ion, and here we should write 2 electrons are also ejected out, because one of the electron is ejected from this molecule. Okay, and I have written 2 electrons. So one of the electron, it is ejected by the molecule, and another electron, another second electron is the electron after bombardment, it get reflected. So this is one electron is ejected from the molecule, Another electron is the reflected electron. This is the reflected electron. Now, so further, this molecular ion at 70 electron volt, that would be undergo fragmentation. Suppose various fragments, either 2 fragments, 3 fragments, 4 fragments, and so on. It could be converted into various fragments, and this is finally detected by these fragments are detected by the mass analyzer like this. Okay, so finally we'll get the spectrum, and spectrum is in this way. Suppose spectrum we get between a mass by charge, this is mass by charge ratio on x-axis, and relative abundance, percentage relative abundance on y-axis. Abundance. So this mass spectrum we get between percentage relative abundance and mass upon charge ratio. Now, so how? So first of all, this is the molecular ion, and this molecular ion is the mass of this molecular ion is exactly same as that of this neutral molecule, because after the removal of one electron, the molecular mass will not differ. And suppose if it has only plus charge, then here Z will be 1. So it has a one charge. So always m by z, this ratio is equal to the molecular mass of either this one, because z remains 1. Here in all cases 1 plus charge, 1 plus charge, 1 plus charge, 1 plus charge. So z always remains 1. It means here on x-axis we are getting the molecular mass of either this. What I told you, it only detects the cation. These are the cations. This is one of the cation, another cation, another cation. So this is the complete molecular ion. This is a fragment ion. When molecule is undergo breaking. So then I will give you the example. Further, I am giving the example to understand you more. So this undergo breaking, and we will get the spectrum. So it has the highest molecular mass is the molecular mass of molecular ion or parent ion. So somewhere means the highest molecular mass will be on the right side of this x-axis. Suppose this is the one of the molecular ion. This is the peak that we get for the molecular ion. Another rest of the peaks we will get for these ions. Suppose this is one of the peak. This is suppose for M1. Suppose this is for M2. This is for M3, and like this. So these are the fragment. These peaks are for fragment ion. So the molecular mass, if from this spectrum, so this peak, the peak which is on the right side of the spectrum, this will tell you the molecular mass of the compound, molecular mass of unknown molecule. And this rest of the peak, it gives you the information, other information in the molecule. Either some benzene ring may be there, some other ring may be there, okay, some aliphatic chain may be there, like this. So this is the main introduction. And suppose let us take one of the example. If I take one example, suppose I fragment one of the molecule. Suppose I take the example of hexane. Now this is hexane, our neutral molecule. First of all, what I told you, this should be converted into gaseous form. It should be vaporized, and here the molecular mass, this is suppose 86 is the molecular mass of this, and this is now converted into the molecular ion at 10 to 15 electron volt. So this is converted into in the form of, if it is bombarded with electron, then that would be converted into molecular ion. And the molecular ion for this is written like this. This is the molecular ion. Means one of the electron from this molecule is removed to give the molecular ion. So how, I will tell you. So now it is further undergo fragmentation at 70 electron volt. At 70 electron volt it will undergo various fragmentation. So the molecular mass of this and this, so this is our molecular ion or parent ion, whose molecular mass remains same as that of this neutral molecule. So after removing one of the electron, the molecular mass will not change. Okay. So now this would be converted into various fragments. This would be converted into various fragments. Now the fragmentation may takes place from various places. Suppose the fragmentation may occur from here. This is the place the fragmentation can occur. This is the place where fragmentation can occur. From here the fragmentation takes place, like this. So various fragmentations are possible at various places. Now if the fragmentation takes place from here, suppose from here, so what we may write it? We may write it in this form. CH3. So after removal of electron, so suppose the electron is removed from here, sigma electron is removed. So what I have given is sigma electron is removed. So after the removal of electron, this positive charge is present over here. Positive charge is present over here and one radical. What we may write, one of the fragmented part, this is the cation and another is the radical. Okay, so this cation and another part is this methyl radical. So two methyl radical. Now the mass analyzer, it will detect only this cation. What is this? This pentyl cation, and this will not detect this methyl radical. So here this the molecular mass for this molecular ion, that is radical cation, is 86. Now after subtracting this 15, so this methyl radical has a molecular mass 15. 12 plus 3, that is 15. Now after subtracting this 15 from this 86, what we will get? Here we will get 71. So here this m by z value, m by z for this will be 71. Now next fragmentation which is possible, next fragmentation is possible from here. Suppose I fragment it from here. This is the another possibility. So here again, after fragmentation, after bombardment of electron, one of the electron will be ejected from this sigma bond. So here this again we may write this is plus and this is radical. So it would be fragmented in this way, and another fragmentation just we may write, that is butyl cation. This is the butyl cation, and next one ethyl radical. So what would be the m by z value for this? The m by z value in subtracting that is CH3 and CH2, molecular mass of this one from 86. So molecular mass for this is 15 plus 14, that is 29. Subtracting 29 from here, so we will get what? Subtracting 29 from here, we will get the 57. Okay, we will get 57. This is the m by z value for this. So the mass analyzer will detect only this radical, this cation. It will not detect the radical. Next fragmentation which is possible, here. Suppose this is positive and this is. So what we may write? Propyl cation and propyl radical. This is propyl cation plus propyl radical. So the mass analyzer will only detect this cation, it will not detect the radical, and m by z value for this would be subtracting now, again subtracting how much? 14 from here. So if we subtract 14 for this, 1 foot CH2 is added over here. So 14 from 57, so this would be 43. Another fragmentation which is, this is another fragmentation, possible fragmentation. So what we may write? We may write the ethyl cation plus butyl radical. So mass analyzer will now only detect this ethyl radical, it will not detect the this butyl radical. So m by z, what would be m by z value for this? M by z, again subtracting this CH2, that is 14 from this this value. So subtracting 14 from here, so 14, that is 29. Subtracting 29. And last fragmentation, it may be possible from here. It is plus this one. So CH3 means methyl cation, and next one, that is pentyl radical. Pentyl radical would be the next one. Now, so this methyl cation having the m by z of 15. Now, so what type of spectrum here we will get? So spectrum, if you will see the spectrum, then spectrum will look like this percentage relative abundance and m by z value. Now what I told you, the mass analyzer will only detect this cation or cation radical, we can say radical cation and these cations. So m by z, z for each fragments or molecular ion is 1. Only if one positive charge is over here, so z is 1. So this m is that is molecular mass for this all fragments or this one. So here the 86 is the molecular mass of this cation. So one of the peak that we may get, this is one of the peak that is at the right corner of this spectrum, is 86. Suppose this is the peak at 86, which is the molecular ion peak. Now next one, suppose this is M1 plus, this is next fragment M2 plus, this is next fragment M3 plus, this is next fragment M4 plus, next fragment M5 plus, like this various fragments that mass analyzer will detect. So next one, that is this pentyl, another peak that we may get is the pentyl one. Suppose I get here one of the pentyl. So this is suppose 71. Next peak for butyl cation, suppose I get the peak over here. So this is at 57. Another one 43. So this is the next one 43. Next one suppose 29. This is 29. So such type of radical and many more lines at this right of this. Some more lines may be there. If you will see, more lines may be present, and these lines, these are the, we can say, these are due to the isotopes. This may be due to the various isotope of carbon here, because this carbon may have some isotope like carbon 13 isotope. Hydrogen may have some isotope, deuterium. So due to that, some other peaks, and we know that this the relative abundance of carbon 13. If we have complete carbon 13, then relative abundance of carbon 13 is very less. So that's why the relative abundance, that in comparison to this this molecular ion peak, the isotopic peak, these are called the isotopic peaks. And isotopes has the relative abundance of isotopes are very less. So that's why the height of this peak the height of this isotopic peak will be very less in comparison to this one. In the same way, the height of suppose 71, so and at 71 another peak may appear at 72, which is the m+1 peak, that is the isotopic peak, and we know that the relative abundance of isotopes are very less in comparison to the main atoms. So that's why these peaks are, the relative abundance of these isotopic peaks are very less. Okay, so we are not here we are not mainly concerned with these isotopic peaks. These isotopic peaks are very much important where suppose chlorine is present in a molecule and bromine is present in a molecule, then isotopic peak it matters. But here in this case the isotopic peak doesn't matter, so I will discuss more about the isotopic peak in my other lectures. So these are the different. Now I have not mentioned the peak of this methyl cation. So because this methyl cation, if you see the books, then in methyl cation it doesn't show the peak due to the methyl cation, which may appear at here, that is 15 m/z value, which may appear. So this peak doesn't appear. Why? Because we know that the methyl cation is a very unstable one. So this is quite unstable. That's why the peak due to this will not appear. This is quite unstable. Clear? So peak due to this will not appear. Now, so this is called as the molecular ion peak, which tells about the molecular mass of the compound. So this peak is a parent ion peak or molecular ion peak. Whereas one of the peak has the highest height. So if you will see, then this peak has this relative abundance, percentage relative abundance. This peak has the highest height. So this peak which is having the highest height, that is called as the base peak, and its relative abundance is taken as 100. It is the abundance is taken as 100, and relative to this base peak, the relative abundance of other peaks are determined. So relative to this means relative to this base peak, the height of other peaks is determined. Suppose the relative abundance means height of this peak is mentioned in relative to this base peak. Suppose it is 100, then this would be suppose 40. This would be 40. This would, relative to this, that is, if it is taken as 100, then this would be taken as suppose 75 or 80. Relative to this, suppose it is 100, then this is taken as suppose 30. So this is that's why we say that this is a relative abundance. And this relative abundance, it also tells the stability of molecular ion, or stability of the fragment ion or molecular ion. So if the height is less, it means stability of the fragment ion. These are the fragment, these peaks are due to the various fragment ion. If height is less, it means stability is less. That's why the mass analyzer is not able to detect so much. So if height is less, it means its abundance is less, its stability is less. If height is more, it means its stability is more. That's why the analyzer is detecting very easily highest detection over here. So if you will see what I have, the relative abundance of this butyl cation is highest. Why? So the height of this peak, it depends upon the relative abundance of this base peak, it depends upon the stability of this radical, is this cation, as well as the stability of the radical which is formed after the fragmentation. So if you will see, then this is not the base peak. This is not the base peak. This is not the base peak here. This is written as a base peak. Why? Because the stability of this butyl radical is more. Here the stability of this pentyl cation is more, but on the other place the stability of this methyl radical is very less. That's why this is not the base peak. But here the stability of butyl radical is more and ethyl radical is on, we can say this stability is not very low, but this is medium stability, we can say. Here the stability of propyl radical is less than the stability of butyl radical. So this butyl radical, so the overall the height of this peak, this depends upon these two, cation as well as the radical which is formed like this. So in mass spectrometry, we will discuss the spectrum of, this is the spectrum of hexane. In a same way we will discuss the spectrum of other molecules. We may have suppose alcohol, we may have suppose acid. So in alcohol the fragmentation is different, in acid the mode of fragmentation is different. In the same way, if we have ester, then mode of fragmentation is different. So mainly in mass spectrometry, we are only concerned with the fragmentation, how the fragmentation takes place. So this is the main part of the mass spectrometry. So if we understand the fragmentation, then we can draw the mass spectrum, rough mass spectrum of that also. So now, so let us see the instrumentation part. So general, I have told you how we can detect the onion molecule in a mass spectrometer. Now, if you will see the instrumentation part, then let us tell you the instrumentation. Now the mass spectrometer, the block diagram, if you see there is the diagram for this mass spectrometer is something like this. Now suppose if we have a molecule, and this molecule should be, what I told you, this molecule should be a neutral molecule, means either in a solid form or liquid form, or it may be in a gaseous form. So if it is gaseous form, if it is in gaseous form, we no need to vaporize it. If it is in a liquid or solid form, first of all we vaporize it. So first part is the vaporization. So first of all it is vaporized. If solid or liquid, then it is vaporized in presence of, suppose this is heating coil. So this is the heating coil, and this heating coil, it will vaporize it. So this is, we may call it a vaporization chamber. Now after vaporization, so this is suppose slit A, this is slit A. After vaporization, this is then ionized, then it is ionized. Suppose this is slit B, this is our slit B. So if we have this various molecule, neutral molecule, here it is ionized, and this is called as the ionization chamber. Ionization chamber, and this is ionized in presence of energetic beam of electron, and which is the source for this energetic beam of electron. This is our tungsten filament. This tungsten filament is over here, and at 10 to suppose 15 electron volt, and further at 70 electron volt, suppose this overall means from it develops a 70 to 10 to 70 electron volt voltage, and this will be first converted into molecular ion after the ejection of electron. After the ejection of one electron, it would be converted into molecular ion or parent ion, and this further at 70 electron volt, it would be converted into various fragment ion, M1 plus, M2 plus, M3 plus, and so on. It would be converted like this. And the next part is the accelerating chamber. So this is vaporization chamber, ionization chamber, and then this is next one is the accelerating chamber. So here we have a electrode. This is the electrode, and here this electric field, actually in presence of this electric field, this has the electrode, and these positive cations, they will move into this accelerating chamber, and these electric field has this negative charge over here, and as we move here, the negative charge intensify over here like this. As we move further, the negative charge intensify like this. Okay, these are the negative charge over this electrode. Now, so that the positive ion may accelerate and go towards this negative charge. So this is also called as the accelerating chamber. This is called as accelerating chamber. And now finally it will go into this mass analyzer, and this mass analyzer, they have a strong magnetic field. Suppose this is the magnets, these are the magnet, and magnet having, suppose this B is the magnetic field for this magnet, and it will deflect into this, and this is also called the mass analyzer. This part, this mass analyzer containing this magnet. So it will go into the mass analyzer, and it will deflect it into this mass analyzer. Okay. So after deflection, suppose it will go like this. Various fragments will undergo. It will go in this way, various fragments. So some fragment will reach the detector late, some fragments will reach earlier, depending upon their mass, depending upon their stability. Some fragments will reach the detector and little earlier, some will reach it late. So here we can see this deflection is less and this deflection is more. So suppose this is the radius. It means after going from this accelerating chamber, it will follow a circular path. This is a circular path, and suppose this is the center of this circle, and here this ion is suppose having the radius r1. This ion is having the radius suppose r2, and so on like this. So r1 is less, r2 is more. So if means this ion, suppose this is M1, this is suppose M2. So M1 is having the radius R1, M2 is having the radius R2. So M1 is more deflected, M2 is less deflected. Okay, so radius is less means it is more deflected. Radius is more, it means it is less deflected. Okay, so like this. And finally, after here, it will go into the detector, and here the signal will get amplified. This is our amplifier, and after this amplifier we have the recorder. Recorder will giving the mass spectrum between relative abundance and M by Z value. So like this we will get the mass spectrum. Now here this instrumentation part, it contains two main parts. One is the accelerating chamber, another is the mass analyzer. Now in accelerating chamber, if you will see in accelerating chamber, where the ions are accelerated, it are moving. So these ions, okay, having the charge Z. So the potential energy of this charged ions, that is equal to the kinetic energy over here. So this potential energy, which is suppose ZV, which is the potential energy, V is the voltage over here. So this is equal to the kinetic energy mv square, and whereas this v is the this is kinetic energy. V is the kinetic energy, and ZV, this is the potential energy. Now here, from here we may determine this V square. If you will see, then V square is equal to 2ZV upon M. This is one of the relation. Now this is in accelerating chamber. Now in mass analyzer here, where the ions or these charges, they are taking the circular motion. They are in circular motion. In mass analyzer, the centripetal force that will be equal to the, as it is in circular motion, so this centripetal force, this is equal to the centrifugal force. Centrifugal force, and which is equal to the centripetal force. Okay, so centripetal force, that is equal to the centrifugal force. So ZVB, that is equal to the mv square upon r. Now from here we can determine this V. So this V, that will be cancelled out, and this is equal to ZRB upon this M. Now putting this value, suppose this is first and this is our second, and putting second in first, we will get this Z square R square B square upon M square. This is equal to 2ZV upon M. Okay, so this is, then we take the square of this and put here over here, and we are getting this relation. So finally what we can say, this will cancel out, and this will cancel out. Now, so what we can write, M by Z value, what we have to determine, we have to determine the M by Z value. So M by Z, this is equal to B square R square. Okay, this is M by Z, this is equal to V square R square upon, okay, so this is equal to 2 okay, so M by Z, so here this M and this is Z, M by Z is equal to R square B square upon 2V. So this relation, we are getting this relation. Okay, now from here what we can see? From here we can see that this M by Z, this is directly proportional to this R square. M by Z is directly proportional to R square, and R is, if radius is more, then deflection is less. If radius is less, deflection is more. So this is directly proportional to this, or we can say deflection. So if radius is less, deflection is more. Radius is more, deflection is less. Then we can see from here. So by this relation, we may see, according to the mass, we may see the deflection, means which ion, which fragment will reach the mass analyzer late, which will reach the mass analyzer earlier, like this. So this is the instrumentation of mass spectrometry. In my next lecture, I will discuss the various ionization techniques. So how the ionization takes place.